Welcome back, ladies and gentlemen. It is Friday, last day of the week. Real quick, short lesson here. Before you start, make sure you have watched this video. It should be linked on my lesson plans. So make sure you watch this video to help further explain the relationship between pressure, temperature, and volume. This guy has a really great example with a sheet of paper that you can follow along with, and it should really help you with the concept of pressure, temperature, and volume and their relationships. The last formula we're going to look at this week is Charles's law for temperature and volume. A guy named Charles, a balloonist, oddly enough, discovered this particular policy, or at least came up with it. He noticed that the volume of fixed mass is directly proportional to the Kelvin temperature, not indirect, like Boyle's law. The temperature must be in Kelvin. The reason why that is, if you look at our formula here in a second, if your temperature was 0 at the bottom of one of these fractions, it would not work at all. So that's one of the reasons why we convert all of our temperatures to Kelvin. Your formula at the bottom reads V1 over T1 is equal to V2 over T2. To help you remember which law this is, Charlie Brown has a lot of specials, particularly his Christmas special is oddly famous, is very famous. So you have Charlie Brown's Christmas was on TV for temperature and volume. Just remember it's V over T. So we look at this particular section. We add energy. You start to see that the volume goes up. So as you increase temperature, volume will go up. That's a direct relationship. Examples of this you've seen, or you may have particularly seen, are ping pong balls and balloons. I'll explain the balloon one first. Helium is stored at a certain cooler temperature, and it keeps that cool temperature for a while. But if you've ever kept a helium balloon around in your house after a birthday party or celebration for a couple of days, you start to notice it starts to kind of drag along the floor, and it starts to kind of condense on itself. That's because what ends up happening is that the helium expands and creates little leaks inside the balloon. So that's why it starts to fizzle down and float down. The ping pong ball is actually a really good story. There's going to be a set of experiments you look at one of these with. The ping pong ball was of course a normal ping pong ball beforehand. And what ended up happening was that they put this ping pong ball in some boiling water. So what they ended up doing, expand the ping pong ball, got to a weird egg-like shape. Well, then this person then took that ping pong ball from boiling water and put it into ice water. The change in temperature was so vast, all of the gases that were heated up inside the ping pong ball shriveled down and got really, really close together, and it sucked the volume in. So as you saw there, you sharply decrease the temperature, you ended up decreasing the volume inside the ping pong ball. Here's our example problem for Charles's law. As we read through the problem, we see a sample of gas has a temperature of 15 degrees Celsius. So I'm going to go ahead and underline that. And 1 ATM. Now remember, 1 ATM is a unit for pressure. We'll come back to that in a minute. Has a volume of 2.58 liters. What volume will this gas occupy at, let me find another color, at 38 degrees Celsius and 1 ATM. So as you get started here, you start to recognize your variables. You kind of probably already know your unknown. The main thing you have to look at here is that you have a pressure of 1 ATM in the front and a pressure of 1 ATM at the end of it. That means the pressure is constant. It means we don't have to worry about it for Charles's law. And we just went over Charles's law, it only deals in volume and temperature. So let's go ahead and start writing out some givens. Our first given that we were given was a temperature. So T. And as we read the problem here, you start to look at it. The temperature goes from 15 to 38. So our T1 here ends up being 15 degrees Celsius. But remember, we don't want to be in Celsius. We want to be in Kelvin. So you need to add 273. And from there, we get our value of 288 Kelvin. Our next given, besides pressure, which we've already discussed is not necessary, is our first volume. Now, this is the first volume because if you look at the problem again, it is paired up in the same sentence, in the same language as 15 degrees Celsius as our previous temperature. So it's not just V is V1. V1, that's going to be equal to 2.58 liters. Our final given that we have, is our change of temperature. So we already have our T1. So let's go ahead and go to our T2. And the T2 is 38 degrees Celsius, but once again, cannot be in Celsius. So we're at 273. We'll go ahead and move that to the right side of our chart here. And we add that together, we get 311 Kelvin for our temperature. Our unknown is easy. Our unknown, we're going to represent with the letter X or question mark, however you want to do it on your problem. But that value ends up being what we're missing. In this case, it's our, if I can put this in red, my apologies. X ends up being our V2. Again, got to be red, V2. The equation for Charles's law, I'm going to write it out, so my apologies for handwriting, is going to be V1 over T1 is equal to V2 over T2. So as we go substituting here, let's go and take a look at it. We're going to start with V1. Our V1 is 2.58 liters. That is over our T1, which in this case is 288 Kelvin, equals V2. We don't know our V2, so that's X over our T2, which is, 311 Kelvin. From here, if you've done proportions or anything like that for math, this is the same thing. I remember when we first started stoichiometry, a lot of you wanted to cross multiply. Well, here's your chance to do so. So now we're going to put this in a different color. We're going to cross multiply these two. I'm going to do my calculator on the side here. 2.58 times 311. I have 802.38. Then on the other side equals 288x. So now I want to get x by itself. So I'm going to divide by 288. Divide by 288. Remember, do not round until the very end. So I got me an answer, and I'll write this out in text. This way y'all don't have to struggle to read it. 2.7 8, 6, yada, yada, yada. We look to our problem. The smallest amount of sig figs we end up having, sorry, we're looking at our substitution over here, excuse me, end up having is 3. So we're going to round this to 3 sig figs. The third sig fig is the 8. The 6 does round that 8 up. So that's 2.79. And then we're looking for our V2, our original, if we look back here, our original unit for volume was liters over here for liters. So we're just going to go ahead and put liters there. If you have to find for temperature, make sure that your answer is the same as any other temperature that we're using right now. It has to be in Kelvin, not Celsius. So make sure you look to your units, make sure for that. Once again, my office hour is from 10 to 11 a.m. for chemistry. If you need more additional help, just let me know.